നമുക്ക് ഇന്ന് ഡിസ്കസ് ചെയ്യാനുള്ളത് സെക്ഷൻ 3.8 ആണ്. So first we can see the definition of lattice point. Definition lattice point. An ordered pair AB is said to be a lattice point if and only if A, B are elements of Z. So this is the definition of lattice point. We have another definition, visible lattice points. Visible lattice points. When do we say that two lattice points are visible? So that is if P and Q are visible if and only if there is no other lattice points other than P and Q lie on the line segment joining them. Okay, so this is today's topic. We need to find a characterization for visible lattice points with respect to their coordinates. Theorem says that theorem, let P the point AB and Q point M comma N be two lattice points. Be two points when P and Q are mutually visible if and only if A minus M comma B minus N equal to 1. That means GCD of A minus M comma B minus N. So this is the theorem. This is the characterization for mutually visible lattice point. So first we need to know the reference. The reference is that suppose we have 2 points in the plane. Then what is the I would say this is some P. This is our Q and this is comma N, A comma B. So P and Q are said to be mutually visible. That means there is no lattice points in between these two. Yep. Suppose we shifted the origin from this point to this point, you'll get shifted the origin to this point. we can say that now this point P is or this point is visible from origin. So this coordinates mn is changed to, you can say that mn will change to m minus m comma n minus m. Okay? And the corresponding AB is changed to uh, a minus m comma b minus m. Okay? So this AB is mutually visible from Mn uh, if and only if this a minus m comma b minus n is visible from origin. Okay? We need to find a characterization for the visibility of AB and Mn. Instead, we will find the characterization of the visibility of this point from origin. If you prove a minus n comma b minus n is visible from origin if and only if these are relatively prime. Okay, that is equivalent to the statement a p and q are mutually visible if and only if a minus n comma b minus n is equal to 1. So we restate this theorem. Restate. Restate the same theorem. Uh, let uh, let p comma ab is a lattice point. Lattice point. Then we write p is visible from origin if and only if GCD of a comma b is equal to 1. Once you prove this theorem, you can say that AB and Mn are mutually visible if and only if GCD of A minus M comma B minus N is relatively prime. Okay, that is obtained by shifting the origin to this Mn. Clear? So we first prove this theorem. As a consequence, you will get this one. For the proof, firstly revise some result from the analytic geometry, the equation of lines. Yes. What is the I will put it as reference equation of line passing through origin and, okay, so equation of line passing through origin and point A comma B. That is always uh, R equal to, that is R is equal to 0 0 plus t times A comma B. So this is the equation of the line. Okay. R is an arbitrary point on the line xy. So we'll get a general or parametric equation as x equal to a t and y equal to, okay. This is the equation of the line. This t belongs to R. This is the equation of the line passing through a origin and a comma b. Okay, when you put t is equal to 0, you will get origin itself. When t is equal to 1, you will get AB. That means for every other value in between 0 and t, 0 and 1, you will get the points in between 0, 0 and AB. Okay, so we can say that xy if xy lies on the line segment joining 0 0 and AB, then x equal to AT y is equal to BT with 0 less than t less than or any other value in between 0 and 1. You will get the points on the line segment joining this diagram. This is an important reference. So you must keep in mind. Now we will prove. So we will prove the theorem. So we need to prove. Let need to prove P is visible from origin if and only if GCD of AB is equal to 1. Okay. So first we assume that P is visible from origin. Okay. Is the point AB. Suppose AB is visible from origin. To prove GCD of A comma B is equal to, suppose if that GCD that is equal to D is not equal to 1, then the only possibility is this is greater than 1. Okay, what happens this is greater than 1? Then you can write this A can be written as some A prime D and B can be written as some B prime D. Okay, so uh, this implies that A prime comma B prime belongs to the line segment joining 0 0 and 0 0 and AB. This is using this reference. We know that whenever you write x equal to AT, comma y equal to BT, with this condition, you can say that this x and y are x comma y lies on the line segment joining these. Clear? So here you can write A prime is equal to A by D. That is 1 by D times A. That 1 by D is always less than 1 because D is greater than 1. Clear? Here you can write B prime is equal to 1 by D times B. That 1 by D is again less than 1. So you can write this A prime and B prime in such a way that some constant times A, that constant is less than 1. Okay? Similarly, B prime can be written as a constant times B, that quantity is less than 1. Okay, so this shows that these these coordinates or this point lies on the line segment joining these two. Okay, obviously this A prime and B prime are integers. Okay, since this D is greater than 1, this A prime does not coincide with this A. Similarly, this B prime does not coincide with B. Okay, so you can get a lattice points other than this A comma B and 0 0 such that A prime comma B prime or that lattice point lies on the line segment joining this. Okay, this shows that these 2 points are not mutually visible. That means AB is not visible from, so this implies AB is not visible from origin. So this is a contradiction. You already assumed that this P is visible from origin. Okay. For the converse part, we assume uh, GCD of A comma B is equal to 1, and we need to prove that uh, AB is mutually visible from origin. Okay? So for that, uh, we will show that there is no other lattice points lies on the line segment joining 0 0 and AB. For assume so if there is a lattice point AB lies on the line segments joining AB and 0, 0, we can write this A prime as T times A and B prime as T times B with 0 less than T less than 1. Okay? So we can say that this A prime and A are A prime B prime is a lattice point. A comma B is a lattice point again. So this A prime and A are integers, B prime and B are integers. Okay? Hence, from this you can write this T is a rational number. Okay? Because T can be written as A prime divided by A, and from this you can write T is equal to B prime divided by B. Okay? One of these equations you can say that this T is a rational number. Okay? Hence, T is a rational number less than, which is less than. Now, T can be written as some R by S, okay, where GCD of R comma S equal to 1. What is the importance of this R and S? Since T is less than 1, S is strictly greater than R. Okay, so we will write this. From this you can write A prime is equal to R by S times A. B prime is equal to R by S times B. Consequently, S A prime is equal to R A, and S B prime is equal to R P. So this implies S divides, obviously S divides LHS. Yeah? So S divides this R A and S divides R B. But we know that GCD of S comma R is 1. So this implies S divides A and S divides B. So that implies S divides GCD of A comma B is equal to 1 plus S equal to. This is a contradiction. Why it is a contradiction? We have assumed that this T is less than 1. Okay, so this R must be less than S. Okay, R must be a positive integer which is less than S. That is not possible because S is 1. If S is 1, then the only possible value of this R is 0 as a non-negative integer. So this that integer should be greater than 0. So that there is no possibility for this R. So there is no such T exist. That means there is a contradiction. Clear? There is no other lattice points lie on the line segments. Okay, this is the theorem.